Life on Earth is sustained by energy from the sun and atmospheric gases that keep that energy within a range conducive to vegetative and animal evolution and sustenance. Gases such as carbon dioxide and water vapor are called greenhouse gases because they, along with the sunlight, support photosynthesis in vegetation. The vegetation emits oxygen required for respiration in animals, including Homo sapiens, as well as providing food for their sustenance. Compared to the atmospheres of other known planets, Earth's greenhouse is unique as far as we know. But we do know that it is in danger. In his most recent book, Jared Diamond notes that nuclear winter and global warming are the existential issues of our time. The word existential is often used too loosely, but the fossil and geological record indicates that periods of extreme cold or extreme heat wiped out much of the life on the planet on 5 occasions in the past. This time, the potential for both is mainly human-caused. Fortunately, we have no data on nuclear winter. Based on knowledge of the effects of soot and dust from volcano eruptions, simulations indicate the effects of the soot and dust from a major nuclear bomb exchange among 2 or more of the nuclear powers would block solar energy for years after millions, perhaps billions of humans had already died or been maimed from explosions and radiations. Temperatures would drop as much as 20 degrees Celsius in the U.S. and 35 degrees in East Europe and Asia. These temperatures would be hugely lower than the drop in temperatures that caused the ice ages historically. Precipitation would decline an average of 45%, vastly reducing food production. This graph is based on simulations by A.L. Robach and his associates at Rutgers University. It shows expected temperature changes in Iowa 3 years following a large exchange of nuclear weapons explosions. The purple indicates temperatures if a third of nuclear weapons in the U.S. and Russian arsenals were used, and the orange if all of the weapons were used. The agricultural output of the state would be virtually wiped out. This is typical of what would happen to temperate regions around the world, but most grievously in the northern hemisphere. The 2 major nuclear powers, the U.S. and Russia, have more than 6,000 nuclear warheads each, dwarfing the hundreds extant in other nuclear powers. The latter nations are dangerous because some are in the hands of countries whose belligerence could trigger the involvement of 2 leaders in weaponry. Donald Trump recently abandoned the nuclear weapons treaty with Russia that limited the number of weapons each could have available. Vladimir Putin quickly followed. Scientists should take every opportunity to emphasize the dire consequences of nuclear weapons use. The other existential environmental hazard is global warming. I'm sure that you're all aware that the planet's atmosphere, oceans, and lakes are warming due to the accelerated use of fossil fuels, particularly during the past 150 years. This growth has initiated amplifying feedback systems that threaten to accelerate warming even further. Most media reports on warming suggest that the effect is gradual and linear. However, amplifying feedback leads to an acceleration of change in the phenomena in question. Burning fossil fuels has increased the risk of 3 major amplifying feedback effects. Increased heating of ocean, river, and lake waters results in more evaporation of water molecules that retain heat, leading to more evaporation. The cloud formations that result reflect some solar radiation so that the effect is moderated. The albedo effect occurs when the ice sheets and glaciers melt to reveal darker surfaces that absorb more heat that in turn melts more ice. The Arctic tundra contains enormous amounts of carbon dioxide and methane. If it melts and those gases are released, warming will accelerate melting more tundra to a point where the process is irreversible, called the tipping point. In addition to human use of fossil fuels that heat the atmosphere and oceans, setting these feedback systems in motion, There are behavioral feedback systems, such as the use of air conditioning powered by fossil fuels, that increase warmth, leading to more use of air conditioning. An additional behavioral feedback effect is likely occurring because of a warming effect on motor vehicle use. More vehicle use in warmer weather increases carbon dioxide emissions that produce more warming. My interest in this phenomenon was piqued by what I think are mistaken claims about the reverse trend in U.S. road deaths 5 years ago. With some annual fluctuation, yearly road deaths in the U.S. during the past 50 years declined due to a variety of vehicle, behavioral, and environmental changes that I will mention in more detail later. In 2015, the downward trend in death rate per 100,000 population abruptly reversed, increasing by 7%. Later, we learned that it increased again in 2016. When the 2015 data were released in 2016, safety officials at the National Highway Traffic Safety Administration and others, interviewed by the New York Times, attributed the reversal to the cause du jour, increased distracted driving by those using cell phones and other electronics. That didn't make sense to me because those devices were in widespread use before 2015. Indeed, NHTSA's observational surveys showed no jump in drivers' use of electronic devices in traffic during 2015. Handheld cell phone use declined a percentage point from 2014 to 2016, part of a downward trend beginning in 2012. Headset use and observable manipulation of handheld devices changed little. So I asked myself, what else happened in 2015 that could increase road deaths? For one thing, the average temperature in the U.S. increased an average of 1.5 degrees Fahrenheit or 0.83 degrees Celsius from 2014 to 2015. We have known for decades that miles driven and road deaths are higher in warmer months and lower in colder months. Here we see about a 20% variation in miles driven from February to July, year to year. The gray areas are economic recessions. Travel peaks in July and is at a minimum in February. I hypothesized that the increase in deaths in 2015 was associated with increased driving related to the temperature increase. Since temperatures and precipitation vary from day to day and are different among local areas, I looked for daily data on local miles driven and vehicle deaths in local areas, as well as temperatures and precipitation. Since the Federal Highway Administration reports miles driven among urbanized areas and deaths in the Fatality Analysis Reporting System indicates the county of deaths, I assembled two data sets of daily temperatures and precipitation, one including miles and one including road deaths. The files contain data from urbanized areas with populations exceeding 300,000, and the road death file was limited to the 100 most populous counties to avoid instability in data based on smaller numbers. The data on miles driven indicated about 59.5 miles per year on average per person for each degree Fahrenheit increase in temperature. That may not seem like much, but the 1.5 degree average Fahrenheit temperature increase that occurred from 2014 to 2015 would add almost 13.6 billion miles of travel in the urbanized areas studied. The mileage data suggested an additional amplifying feedback on warming may be occurring. More warming leads to more miles driven and more carbon dioxide emissions that in turn contribute to more warming. To obtain the road death rates per billion years of population exposure to specific average daily temperatures shown in this slide, using the Fatality Analysis Reporting System data, I first added up road deaths that occurred on days of the shown average temperatures. To find the number of people exposed to those temperatures, I added up the estimated populations of the counties each day that the temperature averaged the indicated degrees and calculated the death rate for people exposed. Notice that the death rates are strongly related to daily temperature. more than doubling from below freezing to the mid-80s Fahrenheit, and then reverse slightly at the highest temperatures. It is unlikely that small increments in temperature affect driver use factors, such as inattention, alcohol use, etc. Given the relation between temperature and miles driven, the most likely explanation is that discretionary road use is influenced substantially by relatively small increments in ambient temperature. Although we do not have data regarding road use by pedestrians and bicyclists, the lack of protection from weather for them makes such an explanation even more likely. In epidemiological terminology, warming results in increased exposure to road death risk. I did a logistic regression of temperature and other factors in 2014 to see if the correlation held, controlling statistically for other factors. In addition to temperature, the greater risk was also associated with more precipitation, higher speed limits on urban freeways, geographically larger counties, and lower average incomes, but these did not modify the temperature effect. Using the equation based on 2014 data, I estimated the expected deaths in each county during 2015 if temperatures had remained the same on a given day as they were in 2014. Added across all counties, there were a total of 600 more deaths than expected related to the 2015 temperature increase. This 6.2% increase is just short of the 7.1% increase in deaths observed nationally. I also calculated the expected deaths in 2015 if all urban freeways in the counties studied had a 55 mile per hour speed limit, the lowest among the counties studied. Results suggest a reduction of 20% in deaths from the actual number would have occurred from reduced speed limits even as temperatures increased as much as they did. Speed still kills, whatever the weather. When the study was reported in the press, a spokesman for the AAA Foundation was quoted saying that the 2015 increase in road deaths was likely a result of improvements in the economy rather than warming. There's a long history of studies relating fluctuations in road deaths to fluctuations in economic indicators. None of these studies that I have seen test the validity of their models by a split-half design. The most recent of these, by Charles Farmer, regressed time series of deaths on time series of unemployment, the log of miles driven, and calendar year from 1990 through 2015. Mr. Farmer did not use all the data available, so I did so, and estimated the parameters in his model using the first half of the data. This slide shows the coefficients in Farmer's model and the model applied to the first half of the whole data set back to 1976. Notice that the signs reverse on the coefficients of calendar years and logarithm of miles driven. This happens because the two variables are so highly correlated that the coefficients are meaningless. The negative coefficient on unemployment suggests that deaths are higher when unemployment is low, but why would they be twice so in the first half of the data compared to the period Farmer used that included the Great Recession of 2008-2009. This slide shows the fit of the first half model to the full data set. The actual deaths in the second half are not predicted by the model. Deaths did not increase as unemployment declined after the Great Recession and only increased in 2015-2016 when the temperature increased. The model is less than worthless, it is misleading. To get a better estimate of the temperature effect on mileage and deaths nationally and control for risk factors in addition to unemployment, I explored the possibility of using monthly data among U.S. states. Since temperature can vary substantially within states and months, I was concerned about the loss of fidelity using available average monthly temperatures among states rather than local areas by day. I first counted the number of road deaths in each of the lower 48 states during months with a given average temperature, and the number of people in those states when the average temperature was at a given level, and produced a graph similar to that shown in earlier for local areas. The correlation of death rates to temperature held, but with more variance. Since the numbers are large enough using monthly data to examine important subsets of the data, I looked at the correlation of temperatures with deaths of occupants of cars, trucks and buses, and separately motorcyclists, pedestrians, and bicyclists. For population potentially exposed, deaths of motorcyclists and pedal cyclists are rare at average monthly temperatures below freezing, and increase as temperatures rise above that point, then level off at temperatures in the 60s, 70s, and low 80s. But pedal cyclist deaths decline a bit at the highest temperatures. Vehicle occupant deaths other than motorcyclists gradually increase on average as temperatures rise, but accelerate in the 70s and 80s. The trend in pedestrian deaths is less pronounced. I added several control variables in a logistic regression model using the state data. In addition to temperature, precipitation, and unemployment, I included liability insurance expenditures, gasoline prices, number of registered vehicles, percent of registered vehicles that were motorcycles, buses, and trucks, and the median age of the population. The choice of variables was informed by previous research. That research indicates that pickup trucks and truck-based sports utility vehicles that are heavier than most passenger cars increase the deaths of occupants of other vehicles and have higher rollover death rates than passenger cars because of too high a center of gravity relative to track width. Motorcycles have a death rate 34 times that of other vehicles for miles traveled. Trucks, buses, and motorcyclists kill more pedestrians per mile driven than passenger cars. Research on the introduction of required liability insurance by states in the 20th century correlated the requirement with an increase in road deaths, inferring that insured passengers and drivers were less cautious. Road death rates fluctuate inversely to gasoline prices. To test the consistency of model years year to year, I fitted the model to state data for each year separately from 2000 through 2016. The detailed results are too numerous to display in a slide, but the most consistent results can be summarized as follows. There were higher death rates related to warmer temperatures, more trucks as a proportion of all vehicles, and an older population. Deaths were higher when unemployment was up, except after recessions. There were lower fatality rates in states with higher insurance costs and higher gasoline prices. Using the logistic regression equations, I estimated the changes in deaths that would be expected in 2015 if each of the variables was unchanged from 2014, while the others changed, and in 2016 if each of the variables was unchanged from 2015. For each of the predictor variables, I substituted the 2014 value in the equation, leaving the others at 2015 value for that year, or the 2015 value in the 2016 equation. The sum of the predicted deaths among states, shown in this slide, was compared to the actual deaths to estimate the number of deaths that occurred related to the change in prevalence of a given risk factor, corrected for the status of the others. The average annual temperatures among the states in this study were 51.1 in 2014, 53.1 in 2015, and 53.9 in 2016. About 5.3% more deaths than expected were related to increased temperatures in 2015, and 3.7% more in 2016. Reduced unemployment in 2015 was associated with more than a 7.2% less predicted deaths than actual deaths in 2015, and 1.5% less in 2016, contrary to the economic hypothesis. Increased percent trucks of all registered vehicles were related to a 3.6 and 4.3% increase in deaths in 2015 and 2016, respectively. Reduced gasoline prices were associated with a 12.6% increase in deaths in 2015, but an increase in prices related to a 1% decrease in deaths in 2016. Deaths declined somewhat from expected relative to increased insurance expenditures, 1.5% in 2015 and 0.5% in 2016. One of the likely reasons for the difference in correlation of lower unemployment with lower road deaths is the variation in new car sales with economic conditions. I could not find new car sales state by state, but nationally new car sales vary inversely with unemployment as seen in this slide. At least part of the correlation of unemployment and road deaths is likely the increase in newer, safer vehicles on the road as the economy improves. I also looked at temperature and miles driven per vehicle among the states in 2014, 2015, and 2016. The least squares regression of miles driven per vehicle registered indicated 117 more miles driven per degree of warmer temperature in 2014, 137 in 2015, and 145 miles in 2016. When precipitation, unemployment, insurance costs, and gasoline prices were added to the equation, they were not significantly related to miles driven per vehicle. Again, it appears that warming temperatures contribute to increased driving, more emissions, and increased warming in an amplifying feedback cycle. Thank you again for the opportunity to discuss these findings with you. I'll appreciate any comments or questions.